called a combustion analysis problem. I like it. It's the stuff we did yesterday, or yeah, Friday. The stuff we did Friday about empirical formulas and weight percent. That actually is what you're going to see here too. Okay, so parts 2 and 3 really go together. That's why I like doing them together. Okay. So an empirical formula, remember, is in contrast to a molecular formula. The empirical one's the reduced one. So we can come up with these empirical formulas using this sort of problem, okay, from combustion analysis. Now, if you're like me, you think of combustion, you think of burning, and that is actually what combustion is, okay? By definition, combustion is basically, it usually involves heat, I think. I guess it wouldn't have to. Yeah, but just combining something with oxygen, so your products, most of your products have oxygen in them. When you guys did your magnesium ribbon, that was combustion. Okay, you start with magnesium, you combine it with oxygen from the room and form magnesium oxide. Okay. So this is actually called a hydrocarbon. This CHY, it's a compound that contains only carbon and hydrogen. The little X's and Y's, they're to be found out. That's actually the formula of the compound. We don't know what that is. We've talked about balancing equations, and I'm not going to hold you to balancing them using this sort of approach. But literally, whatever the subscript of X is, X and Y is in your carbon and your hydrogen respectively, they have this relationship with the stoichiometric coefficients of oxygen, carbon dioxide, and water. Okay. Bottom line, backing up, bottom line, when you burn a hydrocarbon, you combine it with oxygen and you form carbon dioxide and water. That's it. That's it. Don't worry about the stoichiometric coefficients. So we're going to do a problem where we're burning a hydrocarbon. We're also going to do a problem where we are burning a hydrocarbon plus oxygen, basically a compound that contains carbon, hydrogen, and oxygen. And the stoichiometric coefficients of the moles of oxygen, relative moles of CO2, relative moles of H2O have that relationship with the coefficients X, Y, and Z, which correspond to the moles of carbon, relative moles of hydrogen, relative moles of oxygen. So don't worry about those. I'm just kind of throwing those in there. It's kind of neat, though, to think about. That's how that works. We're not going to do it mathematically like that. Bottom line, what you need to get from this is we burn a compound that has carbon, hydrogen, and oxygen, okay, and we get carbon dioxide and water. Notice that whether it has only carbon and hydrogen or whether it has carbon, hydrogen, oxygen, what are the products? The same. Carbon dioxide and water. Bottom line. So, in this sort of problem, what you need to buy into, and I thought I'd go ahead and just write it up here on the board, is that the conservation of matter. Okay, so we have a hydrocarbon, CH. We're going to combine it with, I don't care what the stoichiometric coefficient is of my O2, that's not the point here, to form carbon dioxide and water. What this says is all of this carbon ends up as carbon right there, okay? And all of this hydrogen ends up as hydrogen right there. I call it kind of counting beans, basically, okay? In a combustion analysis, we have mass, I'll write it into this, we have mass of the thing you burn, we have mass of the CO2, and we have mass of the H2O. That's typical combustion analysis problem. All right. So bottom line, if we measure the mass of the CO2, okay, we can use the molar mass of CO2 to ultimately get to moles of moles of carbon. And then we have moles of carbon here. Actually, here in a minute when we do a problem, you're going to see me kind of do what I did on Friday. Element, moles, so carbon, hydrogen. We'll have the moles of carbon from this mass. We do a very similar thing with water. Focusing on the water, we can get to the moles of hydrogen. Focusing on the carbon dioxide, we get to the moles of carbon. That's it. Now, if it's that second type of compound, and we'll do one of these, if it has oxygen in it, carbon, hydrogen, and oxygen, I'll show you how you do this. The problem's a little bit longer, but you kind of have to back those moles out to grams. You got to get grams of carbon, grams of hydrogen, and basically we're going to subtract that from our original that had oxygen in it. Okay. All right. Cool. Very good. Well, I tried this video and it did not work, but this is pretty good. This is just like a little figure from your textbook, I think it is. This balled up thing looks like C2H. Anyway, this is a hydrocarbon with oxygen. There's our oxygen there in the thing we're going to burn, and here's our cute little oxygens lined up to go ahead and react. So those are true reactants. And then on the left is a picture of the furnace. That's kind of cool. So we're emitting those two at high temperatures. What I think is neat is, and again, what do they produce? Well, you see the water, you recognize the water, H2O, you might recognize the CO2. Those little red things over there, that's just excess O2, excess oxygen that doesn't react. Okay? So what I think is cool is there are a series of scrubbers. One will pick up your H2O, one of the products, and the other scrubber picks up your CO2. So by scrubbers, I mean literally they are a type of material that is specifically absorbent to water and specifically absorbent to carbon dioxide. So all they got to do is weigh that material before and after to know how much it picked up. That's it. That's it. That's how we get these masses. All right. So let's work a problem. So I think I went to, you guys don't have this little box there, okay? But what I like to do is kind of write what's going on here with combustion. If you read the problem, this is just a simple hydrocarbon, okay? And the mass of the hydrocarbon that was put into the furnace is given 0.1888 grams. Completely combusted. So I'm going to just go ahead and say enough. Sometimes I put excess, because we've talked about limited reactants. So we have plenty of O2. When we weigh back the two absorbents, we find that the carbon dioxide absorbent picked up 0.6260 grams. 260. And the water absorbent picked up 0.1602 grams. So that's kind of what we have going on here. All right. We're supposed to come up with the empirical formula of the compound. You know, it's funny how you do problems, the same set of problems over and over as a teacher each semester, and I'm pretty sure in this sort of problem, you check me at the end, we are not going to use the original mass of the stuff. We won't. Okay. So it's like I said before, we're going to take the mass of the CO2, and what you're going to see on the next slide is we're going to go to moles of carbon. We're going to take the mass of the H2O, and we're going to go to moles of hydrogen. And by golly, those moles are going right here. Will they be whole numbers? No. But we're setting ourselves up to kind of like what we did in Friday's lecture. We're going to normalize them into a whole number. So here we go. And I think, I laugh because I will get on you guys if you don't do it, but I don't think I showed calculating the molar mass of carbon dioxide, which is 44.01, I think. So the mass of the carbon dioxide, 0.6260 grams, use the molar mass of CO2 to convert to moles of CO2, 1 mole over 44.01 grams of CO2. Now this is again where if you're working this problem, and as long as you label it as a step, you don't have to write the species in. I'm okay if you just write, forget the CO2, as long as you say going for, well no, I guess you would have to. I think you do have to do that. Okay, so that gives us moles of carbon dioxide, but we need moles of carbon. Don't forget this step. How many moles of carbon are there in 1 mole of carbon dioxide? 1, exactly. Don't blow it off. So one last little conversion, 1 mole of carbon over 1 mole of carbon dioxide. Looks like we're around to 4 significant figures. And I got 0.1422 moles. 0.0, final answer, 0.01422 moles of carbon. Cool. And you wouldn't have to do this, but I just am because I just am. So we're going to do a similar thing with water, going for the moles of hydrogen. So the grams of water was 0.1602 grams of H2O over 1. And I bet you know what the molar mass of water is, 18.02. So then we use 1 mole H2O over 18.02 grams of H2O. Now this is a step where a lot of times, and I'm pretty good about not messing this one up now, but how many moles of hydrogen atoms are there in 1 mole of H2O? 2. Yep. So now we need to introduce one more term, 2 moles H over 1 mole H2O. Looks like 4 sig figs. And I got 0.01778. Okay, moles of hydrogen. So again, it's like what I said Friday. You could stop now and you could say carbon, you have 0.01422, hydrogen, we have 0.01778. Okay, that's not going to work, right? So what we did before was we divided by the fewest number of moles, which in this case is 0.01422. I brought my calculator to do that this time. Or can somebody do it for me? And we see if we get a whole number. If we don't, we just keep working it. Oh, not a whole number, but it makes me smile. Okay, so now we got 1.00 and I got 1.25. So now how can we clean that up?
Multiply by 4.
Multiply by 4, yep. So if I multiply by 4, I get 4.00 for my carbon and I get 5.00 for my hydrogen. And that's looking better. What do you think? So like I did last time, here are what my builds look like. This slide, I don't know if you have anything to fill in, but this in italics says, just to remember as we're working these combustion analysis problems, that the way we worked them was we bought into the fact that all of our carbon in our reactant of interest ended up as carbon and carbon dioxide. All of our hydrogen that we're interested in ended up as hydrogen and water. Okay, so this is just kind of a similar deal. If we divide the moles of hydrogen by the moles of carbon, we get a 1.25 to 1. Scaling it up, like Joshua said, multiplying both numerator and denominator by 4, we get a relative number of moles of 5 and 4. So all that hard work that we covered on Friday is still alive and kicking here in combustion analysis. Okay, well, let's see, recognize because the compound didn't have to find that. Okay, right. Okay, now we need to take it up a notch. The difference between this problem and the last problem we did is, and I went ahead and wrote it down here, this problem contains carbon, hydrogen, and oxygen. Let's see, how do I want to do that? Well, let's see. I think this is going to get messy, but that's okay. You guys can handle it. Let's see, how do I want to say this? If I were to write out the steps, and sometimes I do for your homework, I think I might have for homework hints coming up, but they look something like this. Step number 1, you get moles of carbon like we did before. But when you take moles of carbon and then get mass of carbon. So we don't stop there. Step number 2, we focus on our water, we get moles of hydrogen, and then we get mass of hydrogen. Okay. Step number 3 is you take sample mass and you subtract mass of carbon, and you also subtract mass of hydrogen. That gives you mass of oxygen. Okay, so that's kind of where we're at. And I bet you guys could kind of find your way from there. If you get mass of oxygen that was in the sample that you burned, you can convert that mass to moles. And bada boom, you have moles of everything now. You have moles of carbon and hydrogen from earlier, and now you have moles of oxygen. The reason we can't go for oxygen directly is because we, how does this work? Yeah, well, it's just really confounded because we introduce oxygen as another reactant, and we have oxygen in both of our products. So you're like, dude, that's too complicated. That hurts my brain. Oh, sorry, did you get that? Okay, okay. So it's going to look kind of like we started out with. We're going to focus on the carbon dioxide for the carbon. The mass of carbon dioxide, I didn't write it under the sample, but if you look back to the previous slide, the mass of carbon dioxide in the scrubber was 0.421 grams CO2. We need to use the molar mass of CO2, so 1 mole of CO2 over 44.01 grams of CO2. I can't remember what my builds do. I think they might go to moles, I'm not sure. You guys told me 1 mole of carbon for 1 mole of carbon dioxide. Yep, very good. Now I'm going to use the periodic table and just pick off the decimal number for carbon. So for carbon, we know it's 12.01 grams. Sorry, it looks like I stopped. Didn't do that. I don't know which one I want to show you. If you tack on one more term, this is what I started to say. I'm going to put up one more term. If I put up one more term, 12.01 grams carbon per 1 mole of carbon. That will give me grams of carbon. But as you can see from my builds, I went ahead and resolved that. And I must do one more step to get it to grams. But this is kind of convenient, isn't it? I'm going to start for our second problem, carbon, hydrogen, oxygen, moles of carbon. I'm going to put 0.00957. Okay. So now I'm going to piggyback on that answer. So if I start with, wait, here's the mass. Oh, okay. So we're going to get moles of hydrogen. Sorry about this. So from our water scrubber, it picked up a mass of 0.172 grams of H2O. Use the molar mass of H2O, so 1 mole H2O over 18.02 grams of H2O. Then don't forget this step. It's gotten a lot of us, so there's 2 moles of hydrogen for every 1 mole of water. Okay, looks like I'm going to resolve that to finish up what moles of hydrogen are. 3 significant figures. I get 0.0191 moles. It's like keeping tally over here. Okay. Oh, wait. So now this is where I revisit those moles and go ahead and take them all the way to grams. So we piggyback on that 0.00957 moles of carbon over 1. Now here's where we introduce that term I showed you a minute ago, 12.01 grams of carbon over 1 mole of carbon. 3, check that, 3 sig figs, grams of carbon must be 0.115 grams of carbon. And we do a very similar thing with hydrogen, piggybacking on the moles of hydrogen we had previously is 0.0191 moles of hydrogen over 1. We multiply that by 1.008 grams of hydrogen over 1 mole of hydrogen. Round it to 3 significant figures. So you're looking at 0.0192 grams of hydrogen. I usually don't put those on my table, although I could. I don't know, sometimes I guess it might be helpful, but I'm not doing it this time. But you see where these 2 masses are what I'm going to subtract from my original sample mass to get my oxygen. So that looks like this. The original sample mass, the CHY0Z, was 0.236 grams. So we take 0.236 grams minus our carbon, 0.115, and we also subtract our hydrogen, 0.0192. We don't do a lot of addition and subtraction in chemistry, but remember we round according to decimals. So what that means is, to me, I'm looking at 3 decimals here, 3 decimals here, and a whopping 4 decimals here. And we're always conservative, so we have to go to 3 decimals. Okay. So that's the mass of, we're almost done. So that's our grams of oxygen. Now we need to get those grams into moles. So that's not too bad. We're going to piggyback on that mass. So we put 0.102 grams of oxygen over 1. We look at a periodic table, and the decimal number for oxygen is 16.00, isn't it? Yep. Okay, so we have to use the flipped version of the molar mass. So 1 mole oxygen over 16.00 grams. Round to 3 significant figures. Finally, we're ready to fill in our last moles. So our moles of oxygen is are 0.00636.
I got a 638.
Did ya? Yeah, I did too. Wonder if is that 102 right? So 0.236 or did I use an unrounded value, maybe 0.115 minus 0.0192. So I'm going to use the unrounded value, so I got 0.1018. So if we carry that in and take that divided by 16, yeah, that's not a problem at all. So what we were just talking up here is if you,
If we did it the other way, it'd still be correct.
either way, yep, 0.00638.
As long as we show our work and as long as we round it correctly.
Yes, as long as you round it correctly. So either one of those are correct,
Okay.
unfortunately. This first one just carries an unrounded value from the difference. So, okay. So I bet you're going to be okay either way. So we said, I'm going to go ahead and finish this thought up here then. I'm going to make another column. I'm going to divide by the fewest, which looks like it's at 0.00636. And when you take 0.00957, I get 1.50. What happens if you, so we're going to have to multiply by 2, aren't we? But what happens if you divide 0.00957 by the 0.00638? I got 1.502. So it would have been fine. That was my point. Good. So 0.0191 divided by 0.00636. And I got 3. Okay? We good with that? I know, can you see those? All right, so like I said, does it make sense? We can clean it up if we multiply by 2. We got the halvesies thing going on. Times 2. So that gives us 3, 2, and 6. All right. I'm thinking so. Okay.
Are they all divided by the hydrogen number?
We divided by the fewest, which was oxygen.
Oh, I'm sorry.
Yep. And then this is kind of like I did on Friday. It kind of talks you through a very similar approach, but just kind of writing it differently. So again, with this approach, we recognized that the fewest number of moles was the thing that we were going to actually take. In this case, hydrogen, we were going to take the relative amount of oxygen. In this case, oxygen, we're going to take the relative carbon to oxygen, hydrogen to oxygen. Okay, but I like my columns better. So the empirical formula, dun dun dun, is C2H6O2. Sorry, you know what I mean. C3H6. What? Did I do something wrong?
That's what I got.
Wait a minute.
Yeah, when you've got
I'm
those
being
big
punked.
numbers in a row and you use the oxygen number, shouldn't that be 1 next to it? Or,
No, because you multiplied by 2.
oh, I'm sorry.
Oh, see, I got these mixed up. See this? No, I didn't. That's oxygen.
Okay. The smallest amount is hydrogen, isn't it? Or is it,
The smallest amount of moles is oxygen.
oh, okay, in moles.
Yeah.
Yeah, why is it so high?
You have when you divided by the 636, you got the numbers mixed up. The 3 should
yeah.
be your hydrogen
Oxygen
and the
should
1
be
should be
6.
your oxygen.
Oh, thank you. Thanks, Mike. Whoa.
Okay.
And I bet some of you guys were saying that, like, what's she doing up there? I feel much better. Okay. Okay. Yep, I see what you're saying. So this should be 1.00 down here. Okay, good. And what did we say? This is,
3.
thank you. Now we multiply by 2, and we get 3.00, 6.00 for hydrogen, and 2.00. Awesome. So this is the set that's actually going to show up when we do, it'll be C3H6O2. Oh, goodness gracious. Thanks. All right. What do you think? I'm liking it.
So if we use this approach of the combustion for the other problems on the test, that's okay. You said the approaches are a little different than what we did.
Oh, I see, like the final part. I think all I was saying, the approaches, like I like the column thing so I can see when I'm dividing. I like seeing the relative moles line up like that. And then the other one was just more of a, just kind of a paragraph sort of. You know, either way, as long as you show how you get your relative moles, how you scale them to get whole numbers. That's all we're doing there. Yep, either way is fine. So actually, on your homework, I'm going to show you how this works. In this combustion analysis problem, we could track where the carbon ended up in the carbon dioxide, where the hydrogen ended up in the water. We could track that. But I'm going to show you actually an example where it could be something else. You could be actually combining, I think, something sulfur containing, and you end up with a different sort of product over here that has sulfur in it, and that's how you track the sulfur. But you work it just the same. So I'll kind of show you what that looks like. Does that bring us to an assignment slide? Dun, dun, dun. Okay, so this is what these look like. 343. I was just looking at them. There you are. Okay. So I have pictures to go along with each one of these. So I had time, you know, sitting at my desk. So I made these last semester. So this is kind of what we'd been doing before with a little bit of a twist. So we're burning this hydrocarbon, and the mass of the carbon dioxide in the water is given. And also the repeating unit, oh, sorry, not the repeating unit, the exact molecular mass is given. So we're going to use that here in a minute. 3 things you're supposed to do is come up with the weight percent of carbon and hydrogen in the thing that you burn, the empirical formula, which is the X's and the Y's, and then also what is its molecular formula. So this is what that one looks like. So it looks a little different. When I was looking at this in my office, I'm like, really? There's different ways to skin this cat, and you can kind of see how I did it. I used the carbon dioxide to focus on the carbon first, okay? Ultimately getting the moles of carbon and then to grams of carbon, because the first thing I knocked out was weight percent. You don't have to do it this way. You might just want to throw away my hints, okay? So that gave me grams of carbon. Now, in this case, I went ahead, since it only contained carbon and hydrogen, I got the hydrogen by difference. I did what I'd probably tell you avoid doing, but I think it worked out just fine. So once I got the mass of hydrogen by difference, then I can get right to the weight percent, okay, by taking grams of carbon divided by total weight, grams of hydrogen divided by total weight. Then I had to switch gears, and we're going for the subscripts. We're going for the empirical formula. We actually had the moles of carbon up here, and then this is kind of like what we've been doing before. We get the moles of hydrogen from the water. Actually, we wouldn't have to do that because we have the grams of hydrogen. I don't know if it says my answer key, but you can just go ahead and go from the grams of hydrogen to moles of hydrogen using hydrogen's molar mass. Bottom line, you get relative moles of carbon and hydrogen, and you're kind of back to what we've been doing. Divide by the lowest number to get the empirical formula. Scale up if you have to after you divided. Then for the last one, we actually talked about this sort of problem on Friday, we're like, okay, we got the empirical formula, we got kind of what that repeating unit is, and we have the overall weight of the molecule is 106 AMUs, or atomic mass units, okay? How are we gonna scale this up? Remember, this is where we took the weight it entirely weighs. I have 106 here, I have 109, this should be 106. We take our 106 and we divide it by the individual repeating units. This is kind of like what we might have even had a homework that was due today that did this. Okay? So you're going to get an integer, and then you're actually going to take that integer and you're going to multiply it through your empirical formula. It's kind of like what we did Friday. Okay, so in this one, here comes your picture. This is a hydrocarbon with oxygen. Okay? And you're supposed to kind of do the three things you did before. You're supposed to, and we have the molecular weight. So you're supposed to come up with the weight percent, the empirical formula, and the molecular formula. So it should be kind of similar to the other. Except you're going to have to get your mass of oxygen by taking your sample mass and subtracting your carbon hydrogen to get your oxygen. Okay? Like previous, similar to previous, yeah. Okay? All sorts of fun and games. Now this is the one I was talking about, where actually you're burning something that has carbon, hydrogen, and sulfur. Okay? Notice that we have something on the product side, SO2, only has sulfur. So it's kind of like the approach we've been talking about. All the sulfur in our thing ended up as sulfur as in SO2. Okay? So it's going to be kind of have a very similar cadence to it. All you need to do is get to the empirical formula for this one. You don't need weight percent or molecular formula. Okay? So you'll get relative moles of carbon, hydrogen, and sulfur, and go ahead and normalize them into whole numbers. All right. All right, last one. Last one is I was looking at it. In the past, I've looked at it, I'm like, this looks like a stoichiometry problem, but it's not, because actually we don't know the balanced equation. That's not the point. We're not balancing this equation. Although we could and work it. But you're not supposed to. In this one, we are burning a hydrocarbon, excess oxygen, like we always do in combustion analysis. And you're supposed to come up with what mass of carbon dioxide and what mass of water would that produce. And here's my hints. Okay, I would take the mass of the compound. Now, the full molecular formula of the compound is given. So you can go ahead and use a periodic table and get the molar mass and convert those grams to moles. Once you have moles of that, once you have moles of this is the thing you burned, I would go to moles of carbon in the thing that you burned, which the formula says 4. We have 4 moles of carbon for every 1 mole of C4H10O. Okay? And then I would go from moles of carbon to moles of carbon dioxide, 1 mole of carbon dioxide for every 1 mole of carbon. Okay? And then I would go ahead and use molar mass of carbon dioxide to get the grams of carbon dioxide. That's what I would do. And to get to the mass of water, we focus on first the relative moles of hydrogen in the compound you burned, which looks like 10 to 1. What? My Snoopy? Thanks. And then we go to moles of water molecules. Don't forget, we got a 2 to 1 relationship between moles of hydrogen atoms and moles of water molecules. And then use the molar mass of water to back out to the grams of water.
It's almost like he's playing in a rain shower.
It does look like you're playing in a rain shower. I don't know. So, okay. Awesome. So Wednesday we'll start on Unit 3.